Example 2 that we looked at in the previous video together with Theorem 8.1 also suggests a condition to figure out when the external direct product of two cyclic groups is cyclic. And that's what we're going to look at in Theorem 8.2. So suppose we are starting with two groups, G and H, that are finite cyclic groups, and we would like to write down a condition to say when G plus H is cyclic. And so what has to be true about the order of G and the order of H for G plus H to be cyclic? Well, if the order of G and the order of H are relatively prime, then our group G plus H is cyclic and vice versa. So this is an if and only if condition. We get relatively prime as our condition. And let's talk about the strategy behind this proof before we go about proving it. So here's a Theorem 8.2 scratch work. So let's see. We have G, it's cyclic, so let's say it is generated by A. And then H is also cyclic, let's say it's generated by B. And let's also say that the order of A is, say, M, and the order of B is N. So what we are asking ourselves is, when is G plus H cyclic? So when does it have a generator? And if we have a generator for G and a generator for H, it's reasonable to ask is when is A comma B a generator for G plus H? And let's look at how many things are in this group. So G plus H, the order of that is, the number of things in G times the number of things in H, since we are forming ordered pairs. So this is M times N. And so now we can go back and remember what we learned in Theorem 8.1. So the order of A comma B, that is the least common multiple of the order of A and the order of B. So that's M and N, respectively. And under what conditions is that equal to the order of our external direct product of G with H? Well, that happens to be true if and only if the greatest common divisor of those two numbers, M and N, is equal to 1. So this is the idea behind this proof. So let's write it down. And since it's an if and only if, we have two directions here. So here goes the proof. So let the order of G be equal to M and the order of H be equal to N, so that the order of G plus H is equal to M times N. So this is what we're going to be working with, no matter which direction we're working with. And I'd like to do the backwards direction first. So let's do that one first. So here we have that G is generated by something. So let G be generated by, let's say, G, and H be generated by a little h. And we are supposing that the orders of G and H are relatively prime. So let's write that down and suppose that the GCD of M and N is equal to 1. Okay, so then this is going to be pretty straightforward, because what we're going to look at is the order of G comma H. We're going to show that this is going to be our generator. So let's look at the order of G and H. And by the theorem that we just proved, 8.1, we know what it is. It's the LCM of M with N. So that is by Theorem 8.1. But if the LCM, what is the LCM of M with N? Well, we are assuming that the GCD of M and N is equal to 1, so then the least common multiple is the product of M with N, since they don't have any prime factors in common. So this is M times N. But that is the order of G plus H. And so we see that the order of G comma H is the same as the order of the group. And so that means that G comma H has to be a generator for our group, G plus H. So we have G comma H, our group element, is a generator for our group G plus H, our external direct product. So that is one direction of our proof. Now let's do the other direction. So the other direction, we are, let's go back to the statement, we are assuming that G plus H is cyclic. All right. So assume that G plus H is cyclic. And if it's cyclic, it has a generator. So let's say our group is cyclic with generator G comma H. And we don't know yet what the GCD of the order of G with H is. So let's give it a name. So let's say D is going to be the name of our GCD of M with N. And to prove our theorem, what we need to show here is that D, the GCD, is 1. So that's what we need to show. Okay, let's see how we can do that. Well, let's look at G comma H raised to the M times N divided by D. Okay. So if we are looking at that, this is equal to, since D is a divisor of both M and N, we can rewrite this. This is G raised to the M raised to the N over D. Since D divides N, this is perfectly fine. And we also have similar result for H, but H to the N to the M over D, that's also perfectly fine because D also divides M. It's a common divisor of both M and N. But what is that equal to? M was the order of our group G, and H was the order of our group, N was the order of our group H. And we have a nice theorem in chapter 7 that says if you are taking a group element and raise it to the order of the group, you have to get the identity. So this is the identity element in our external direct product, and the exact theorem for this equality right here, this is Theorem 7.1, Corollary 4, states that this is true. So this means that we have M times N is equal to, well, the order of GH, since we said that GH was a generator of our group. But on the other hand, this is less or equal to now M times N divided by D, because over here we get the identity by raising D comma H to the M times N over D. So let me just write down where these things come from. So that first equality was, since G comma H is a generator, for our group. And then the second one comes from this result right here. Let's call that star. The computation that we just did. So what is this telling us? It's telling us that m times n is less or equal to m times n over d, but that can only be true if d is less or equal to 1. So we have d is less or equal to 1, but d is the greatest common divisor of two numbers that can't be less than 1, so d has to be equal to 1. Because the divisor has to be positive. And it's an integer. And so there we are. We've shown that d is equal to 1. So we assumed that g plus h was cyclic, and we showed that that implies that the greatest common divisor is 1.